Hello. In this video we're going to talk about series and the test for divergence, but before we get into that, let's get an initial building block, which is going to be partial sums. And recall, this all ties back to the preceding video on sequences. But without further ado, partial sums. The definition of a partial sum is the sum of a finite, let's go ahead and underline that, a finite number of terms in a sequence. This finite term here is going to differentiate a partial sum from a series, which we'll discuss next. So before I get to give you the formal definition, let me just give you a quick example. And for example, let's use that same sequence we looked at in our previous video on sequences. It was the sequence where a sub n was going to equal just n over n plus 1. And recall that we found the first several terms of this sequence as shown here. And recall that this right here was A1, this was our A2, this was our A3, A4, etc. Now let's say we wanted to find S4, and that's going to stand for the fourth partial sum of this sequence. So S4 is just going to be the addition of A1 plus A2 plus A3 plus A4. S of 4 is going to be the addition of the first four terms in this sequence. So that's all we mean by a partial sum. It's just the addition of a certain number of terms in the sequence. But to define this a little bit more formally, we can introduce some sigma notation here. But just to finish this problem out, if we go ahead and add those terms up, we're going to get 163 over 60, which we want to convert that to decimal notation. It's going to be approximately 2.7. That's going to be our S sub 4 value. So that's basically what it is, but to provide a bit more of a formal definition, let's introduce sigma notation. So formally, S sub n, where n is the number of terms that we're going to add up, is going to equal the summation of our sequence, where we're going to cycle I through 1 up to our n value. So in this case, see this n up here is going to be the number of terms that we're going to add up. You can see that's what the 4 is here. That's going to be your n value in this one. And the sigma notation, what this is the Greek symbol for basically S corresponding to sum. So this is basically just a simplified way of communicating that we're going to add up a certain number of terms. If we want to write this out a little bit, we could say this is equal to a1 plus a2 plus a3 and keep adding all the way until we get to a sub n. In our case up here, our n was 4, so we just added the first 4 terms, and then once you get to n, you stop adding. So if we were to apply this sigma notation up here, this S of 4, we could just say that is going to equal to the summation from I equals 1 to 4 of I over I plus 1. Notice this is the same as we have up here. I just replaced the n's with i's because that's what we're going to cycle through. And of course our first term is just I equals 1, so it's just going to be 1 over 1 plus 1, which is 2. And this would be another way of saying S sub 4 using sigma notation here. And don't let this sigma notation scare you. It's basically just a simplified way. So you can see that writing this out was a little bit shorter than writing this out. But you could really come to appreciate it more if, say, we had 16 terms, then you're really going to like this notation. It's just a way to save time and energy. So don't let it scare you off. Alright, so this is our partial sum, and having defined that, we can move on to series, which is basically the same thing, except a small difference here. So for a series, our definition is going to be the sum of all the terms in a sequence. So instead of a finite number of terms, instead of that n being, say, 4, it's going to be infinity. So we're going to add up all the terms in a sequence. So for example, we could take that same sequence we just looked at, n over n plus 1, which again we defined as this sequence here. And we can define S. So this S term is going to be our series. It's going to stand for the summation of all of the terms in a sequence. So instead of having these commas in here like we do in a sequence, we're going to add them together. So you could imagine In this case, the numbers are actually getting bigger, right? 4/5 is bigger than 3/4 is bigger than 2/3 is bigger than a half. So perhaps you can imagine if we kept adding an infinite number of terms on the end, s is going to increase without bound, and so we can say that s is going to equal infinity. If that isn't immediately obvious, that's okay. We're going to hit on this a little bit more, but it's going to be an important concept in order to understand the test for divergence. But first of all, let's look at the formal definition of S. So formally, S, our series, is going to equal this same summation term, except instead of having let's go to some n value up here, it's going to go to infinity. So, because it means we're cycling n from 1 all the way up to infinity. We're going to add up all those terms. So if we wrote this out, it would look like this, where we got the dot 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 here to show that we're just going to keep adding and adding. And if I wanted to apply the sigma notation up here to this s, I could say that this s is equal to the sum of n over n plus 1. And you notice I didn't put an n equals 1 down here or an infinity up here. And I didn't put that there because you might see this where that is just left off. And it says if that's left off, you can just assume it's an infinite sum. And the reason for that is, of course, mathematicians like to conserve as much time and energy as humanly possible, which is a politically correct way of just saying they're lazy. But speaking of saving time and energy, let's go ahead and move on. And let's take a look at this from a bit of a different angle. So let's take this, let's move it up, and let's throw a graph in here. Okay, here's a plot, and what I got here is the n values down here. So here we got n equals 1, n equals 2, n equals 3, and 4. And when we had n equals 1, our a sub 1 term, if you remember, was a half. A sub 1, recall that was our a sub 1 term up here, so a half. So our first value we can plot here, a sub 1. Over here we can plot a sub 2 was 2/3, a sub 3 was 3/4, a sub 4 was 4/5. So remember, these are approaching 1, but they never quite get to 1. So now having defined these a terms again, the terms in our sequence, let's look at these partial sum values, and I'm going to go ahead and do that in a different color here. So if we looked at s sub 1, that's just s sub 1 is we're just going to add up the first term by itself. So that's actually going to be the same as a sub 1. So we can call this s sub 1 right here. Now s sub 2 is going to be 1/2 plus 2/3. It's going to be the sum of the first two terms here. So it'd be something up here. So something like that, s2. s3, we're going to take this value for s2 and we're going to go ahead and just add the third term on here, 3/4 to that. So that's going to bump it up something like up here. And recall for s4, we already calculated that. That was about 2.7, so something like right here. This is s3 and s4. So if you recall, our sequence here is sort of going to cap out at 1. But what that means is that we're going to keep adding 1 each time. So s sub 5, we're going to add something close to 1. And so as we keep going further out in the n direction, we're going to get increasingly higher values of s sub n. We're just going to add 1 each time. So you can imagine if you keep adding 1 each time, it's going to increase without bound. This is going to keep this line here is basically, it's going to keep going up. The further we go in n, the further it's going to be. It's going to increase without bound, and therefore we can say that this series value is going to be infinite. It's going to diverge. So this is just maybe sort of a graphical way if it helps you understand why if we keep adding 1 to this, it's going to get bigger and bigger. And this is sort of the basic intuition of the test for divergence. Our test for divergence formally states that if the limit of a sub n or sequence as n approaches infinity, if that limit is not equal to 0, then the series of a sub n will diverge. And the basis of this is essentially what we just discussed. Say if this limit doesn't equal 0, say it equals 1, like in our previous example, we're going to keep adding 1s, adding more and more 1s, and that means that if we keep adding those, this series is going to keep getting bigger and bigger without bound, and therefore it's going to diverge. And that's the basis of this test. But let's go ahead and apply that to our sequence and just to see how it works out. So for example, does the series, the infinite sum of n over n plus 1, diverge? So we found out earlier that this equals infinity. But let's just go ahead and apply this criteria here, look for this limit, see what it equals, and go from there. So first we want to take this limit of a sub n as n approaches infinity. And of course this is going to be our a sub n, because this is our sequence term in the middle of this series. So we take this a sub n term and plug it in for this, and we get this limit. And if you recall, we actually solved this limit earlier in our previous video. It's pretty simple. We're just going to multiply the top and the bottom by 1 over n. And having done that, we get this limit, and of course we can go ahead and apply this limit now as n approaches infinity. This right here term is going to go to 1, this is going to go to 1, and this is going to go to 0. So this limit of our sequence as n approaches infinity is going to go to 1. Now look at our criteria up here. Now we got to see, is that equal to 0 or not? Well, 1 does not equal to 0, therefore our criteria up here is established, and we can definitively say, therefore, the series diverges according to the test for divergence. Alright, so we looked at the test for divergence, gave a simple example. We had looked at series and looked at partial sums, following up our video on sequences. And the next thing we're going to do is go ahead and look at geometric series. So thanks for listening, hope this helps, and take care.